All right, let's dive in. Today, we're going to pull back the curtain on one of the most fundamental ideas in all of modern AI, the neural network. We're actually going to build one, conceptually, from the ground up, so we can really understand how a machine learns to do something that you and I do without even thinking. Okay, so take a look at this. It's a 3, right? No question. I mean, it's kind of sloppy, it's low resolution, but your brain it gets it instantly.
You don't have to consciously trace the lines or think about the curves. Something in your brain just fires and says, yep, that's a 3. It's this incredible, almost unconscious feat of pattern recognition that we do all day, every day.
Now, flip that around. Imagine your job was to write a computer program, a set of hard rules, to recognize that same 3. All of a sudden, this thing that was totally trivial for you becomes this ridiculously hard problem. And that's the puzzle we're going to tackle.
So let's get into what we're calling the recognition puzzle. We're going to use this super simple-sounding task, just recognizing handwritten numbers, to understand the exact kind of problem that neural networks were basically invented to solve.
So why is this so tough for a machine? Well, for starters, think about all the ways you can write a 3. The exact pixel values are going to be wildly different every single time. So trying to define a 3 with rigid if-then rules, well, it's pretty much a recipe for failure. It's just way too brittle. So instead of us trying to write the rules, we build a machine that can learn the rules on its own. So let's open up this so-called black box, a really simple, plain vanilla neural network, and see what's actually going on inside. Okay, the most basic part, the fundamental building block, is the neuron. Now don't let the biological name throw you. For what we're doing, a neuron is just a thing that holds a number. Specifically, a number between 0 and 1. We call this its activation. Just think of it like a little dimmer switch on a light. It can be all the way off at 0, all the way on at 1, or somewhere in between.
So you take a whole bunch of these little neuron lights and you organize them into layers. You've got an input layer, which is where the raw data first comes in. Then you have these things called hidden layers, where all the magic kind of happens. And finally, you have an output layer, which gives us the final answer.
Let's map this out for our number recognizer. Our little image is 28 by 28 pixels, right? So that's 784 pixels total. That means our input layer needs 784 neurons, one for each pixel. Then let's say we have 2 hidden layers. They're the thinking part. For now, they're kind of a question mark. And finally, the output layer has 10 neurons. Why 10? One for each possible digit, 0 through 9. The brightest neuron in this last layer, well, that's going to be the network's final guess.
So we've got these layers, but what are we actually hoping is happening in those mysterious middle ones? What's the grand idea here? What's the goal? Well, think again about how you recognize a 9. You're not really seeing a jumble of pixels. You're seeing parts. You see a loop, and you see a line attached to it. And 8 is basically just 2 loops, one on top of the other. We see the world by breaking things down into smaller components. The hope, the big dream, is that the network learns to do the exact same thing. We want it to build up its understanding, layer by layer, recognizing more and more complex ideas based on the simpler ideas from the layer that came before it. So the perfect process would look something like this. Layer 1 just sees the raw pixels. The next layer might learn to look at groups of those pixels and say, hey, that looks like a little edge, or that's a curve. The layer after that could piece those edges and curves together to spot bigger components, like a full loop or a straight line. And then finally, that last output layer looks at those components and confidently says, a loop and a line, that's a 9. Okay, that sounds amazing, but how does a neuron actually learn to spot something like an edge or a loop? To get that, we need to zoom all the way down to a single connection and look at the simple math that makes this whole thing go.
Every single connection between neurons has 2 little parameters you can tune, kind of like dials on a machine. The first one is its weight. The weight basically tells the neuron how important a signal from a specific input is. The second dial is the bias. The bias is kind of like a threshold. It tells the neuron how high the total combined signal needs to be before it really starts to light up and get active.
So a neuron's first job is to calculate what's called a weighted sum. It's super simple. It just looks at all the neurons in the layer before it, multiplies each of their activations by its own special weight for that connection, and then adds all those numbers together. This gives it a starting score. But hang on, there's a problem. This weighted sum could be any number. It could be 50, it could be negative 100, anything. And remember, our neuron's activation, its brightness, has to be a clean, predictable number between 0 and 1. So how do we fix that?
We use a handy little tool called a squishification function. I love that term. The technical name is the sigmoid function.
all it does is take any number you give it, our weighted sum plus the bias, and it neatly squishes it into that 0 to 1 range. Really negative numbers get close to 0, really positive numbers get close to 1. And just like that, we have our final clean activation value to pass on to the next layer.
Okay, so now that we've seen the guts of a single neuron, let's zoom back out and really appreciate the scale of this thing we've built. So every connection has a weight. Every neuron has a bias. When you add all of those dials up in our quote-unquote simple digit recognizing network, you get almost 13,000 of them. 13,000 individual knobs that all need to be tuned perfectly.
And that, right there, is what we mean when we say a network is learning. It's not magic. It's the long, hard process of finding just the right settings for all 13,000 of those dials, so that when you feed it an image of a 3, the 3 neuron on the output layer is the one that lights up the brightest.
So when you look at it this way, a neural network stops being some kind of mysterious, unknowable black box. It's really just a function. Yeah, it's a ridiculously complicated one, with 13,000 little parameters inside it. But it's a function that takes 784 numbers in and spits 10 numbers out. That's all it is.
We've seen how this structure can, at least in theory, learn to see numbers. But those same core principles of layered abstraction, of building up complex ideas from simple ones, they can be applied to so much more. Which leaves us with a really fascinating question. If a machine can learn to see a 9 by spotting its loops and lines, what else can it learn to see in the world all around us?